What is going on, guys? My name is Amos and I'm back again with another video. So in today's video, we want to talk about le raisonnement par récurrence, otherwise known as the principle of mathematical induction. Now, this is going to be a very important technique to learn to use, as most of the propositions are going to be defined in the form for every n in a certain set. Let's say B, we have P of the proposition P of n. Now, we need to find ways of showing that these propositions are actually true, if they are true, or maybe try to disapprove certain propositions. So what are the steps involved in establishing a proof by mathematical induction? So the first step is to check for what is known as the basis case. So our basis case. So now the basis case is mostly going to be either P of 0 or P of 1. So this basis case is most likely going to be P of 0 or P of 1, depending on the proposition that is given. Now, if the basis case is true, if this is true, then we can proceed to step 2. Otherwise, we end here. It means that our given proposition is false. So if this is true, we move to step 2. Now, step 2 is going to involve what is known as the induction hypothesis, or otherwise known as l'hypothèse de récurrence. So we have the induction hypothesis. All right. Now, this is going to be in the induction hypothesis. We have to suppose that P of n is true. We have to suppose that P of n is true. Then in the third step, we have to show that P of n is going to imply P of n plus 1. Now, this is going to be our mathematical induction. So this is going to be our mathematical induction. So first of all, we have to check for the basis case. If we check for the basis case and find that the basis case holds, or that the basis case is true, then we proceed to the induction hypothesis. So we suppose that P of n is true. And lastly, we need to show that the implication P of n implies P of n plus 1 is true. Meaning here, we've supposed that P of n is true. So our goal will be to show that this is also true. Our goal will be to show that this is also true. Hence, the implication is going to be true. All right. Now, let me give you guys an example so that we understand what we are talking about and we are not lost. Now, the example that I'm going to give you guys is a very common example, and you guys might have already come across this example. Maybe when you were talking about arithmetic and geometric series, or maybe somewhere in your mathematical journey or your mathematics journey, you have come across this problem. So our proposition P of n, I would say, is going to be 1 plus 2 plus 3 plus ... So basically, we are taking the sum of n items. So we show that this is going to be given by n plus 1 divided by 2. This is our goal. We have to show that the sum of n items is going to be given by n multiplied by n plus 1 in parentheses divided by 2. All right. So now, the first thing that we need to show is we need to verify is the basis case. So what is the basis case? So in this case, it's not P of 0, but rather P of 1. Why? It's because I look at the first term that I have here. The first term is a 1. So I try to find my P of 1. So I'll try to substitute 1 into this expression that is on the right hand side. So to verify my basis case, that is, so my P of 1 is going to be equal to 1 plus 1 divided by 2. Now, clearly, this is going to be a 2 divided by 2, which is a 1. So we have that we get a 1, which is going to be equal to the first term of this summation. Now, this is going to verify the basis case, and so we can proceed to the induction hypothesis. So the next thing that we're going to do is to suppose that P of n est vrai. We suppose that P of n is true, vrai, and we try to show that the implication P of n implies P of n plus 1 is also true. So we suppose that P of n is true. So basically, we have that what we've supposed here, our P of n is everything here. So we suppose that this is true. And then now our goal, what is our goal? Our goal is going to be to show that the proposition P of n plus 1 is going to be equal to 1 plus 2 plus, so I can just write this, plus n plus 1. So we add one more term, so which is n plus 1. Then this is going to be equal to n plus 1 and n plus 2. If you substitute n plus 1 into this formula, you're going to have n plus 1, n plus 2 divided by 2, like so. This is our goal. This is what we need to show eventually. So this is what we'll show eventually. So this is going to be equal to, so first of all, I'll keep this in mind. I'll put this in mind. So I'll start with the left-hand side. All right. We need to show that this expression on the left-hand side is going to evaluate to the expression on the right-hand side, right? So we have that this is going to be our goal. So you write this on a rough piece of paper so that you know where you're going. Essentially, as we're going to be working with this. So I'm going to just get rid of this so that you guys do not get confused. But this is our goal. We want to establish this. So I'll just leave the left-hand side. I'll just leave the left-hand side so that we actually follow everything in a step-by-step fashion. So summing from 1 up to n is going to be equal to this n plus 1 divided by 2, because we've supposed that p of n is true. So summing from 1 to n, we can actually we can bring in our formula here. So we can have n plus 1 divided by 2, like so, and then plus n plus 1. Now, if I was to sum these two things, I'm going to get n squared plus 3n plus 2. N squared plus 3n plus 2 divided by 2. Now, the expression on top is a quadratic expression that is factorizable. And if I was to proceed with the problem, I'm going to find that the p of n plus 1, which is equal to 1 plus 2 plus dot dot plus n plus 1, is actually going to be equal to n plus 2 n plus 1, or n plus 1 n plus 2 Celamem shows. So it's going to be equal to this. So I've established that the left-hand side is equal to the right-hand side. If you saw what was indicated in our goal, so we've shown by mathematical induction that p of n plus 1 is also true. So because p of n plus 1 is true, because p of n plus 1 is true, then we have that the proposition, then we have that p of n is true. So we verified that the basis case was true, and we suppose that the proposition p of n was true, which was our induction step. And then finally we showed that the implication p of n implies p of n plus 1 is also true. So this is our first example. Now I'm going to give you guys another example that is going to involve the greater than sign, because you might be thinking, well, we might maybe always have the equal sign. Well, that is not always the case. You might have inequalities, and mathematical induction can do the job as again in those situations. So our second example is going to be for every n in the set of natural numbers, we are going to have 2 to the power n is strictly greater than n. Now, what is our basis case? So that is the first thing that we have to establish. Is the basis case true? So now, what is going to be our basis case? Remember, I said that 0 is sometimes understood to be part of the set of natural numbers, or it is going to be in most books actually that you're going to be studying here. We're going to be including 0 into this set of natural numbers, unless we specify that we are excluding 0 by saying n étoile, for example. Here we only have an n, so 0 is part of the set of natural numbers. All right, so our basis case is going to be p of 0. So p of 0 is, we take n as 0. So if I do p of 0, I'm going to have that I'm going to have that 2 to the power 0 is equal to 1. Now, n is 0, so this is going to imply that 1, now let me just to remove all the confusion. So this is going to imply that 1 to the power 1 is going to be strictly greater than 0. Now this is true, so our basis case has been established. So our basis is true. So we can now proceed to the induction hypothesis. So our induction hypothesis is going to involve, so I'm going to write hype here for our induction hypothesis. So supposons, so we have 2 to the power n strictly bigger than n. So now what is our goal? Our goal is to show that 2 to the power n plus 1 is strictly bigger than n plus 1. So you write this on a rough piece of paper, and then you get your left hand side. So let me just get my left hand side. So 2 to the power n plus 1 is actually going to be equal to what? It's going to be equal to 2 to the power n multiplied by 2 to the power 1. Now for this case, this is also going to be equal to 2 to the power n plus 2 to the power n. So you can easily verify that this is the case here. Now I have 2 to the power n plus 1. Now I've supposed that 2 to the power n is strictly bigger than n. So if I can substitute for 2 to the power n here, so I can put n here, but the sign is no longer going to be the equal sign. It's going to change into a greater than sign. Now if I substitute both of them, I'm going to have 2n. So I won't reach my goal. So I'm going to just substitute one of these guys and try to figure out how I'm going to get the 1. So if I substitute one of these guys, I'm going to have greater than, no longer equals equal sign, because I've substituted something that is less than what we had previously. All right, so this is going to be, and this would work in the same way if you had a less than sign here. You have to put a less than sign if you want to substitute n for 2 to the power n. So we have n 2 to the power n. One thing that is also known as a fact, given this problem, that is for any set of natural numbers, 2 to the power n is strictly bigger than n, is that 2 to the power n is strictly bigger than 1. Well, this is well known. If you take is going to be greater than or equal to 1. If you take 0, you're going to have 2 to the power 0 is greater than or equal to 2 to the power 0 is going to give you 1. So you have 1 is equal to 1. So we have equality when n is 0. For the other cases, we are going to have that 2 to the power n is going to be strictly bigger than 1. So this is also a fact. So I can also substitute this 2 to the power n by a 1. Now the sign is not going to change into a greater than or equal to sign. You already have a greater than sign here. So you're going to proceed as such. So you're going to have 2n. This is going to be equal to, or this is going to be greater than. So we have this. So if I substitute 1 here, I'm still going to have the greater than sign. So well, even though this is a greater than or equal to sign, you already have the greater than sign here. So this is going to give us 2 to the power n. N plus 1 is going to be greater than n plus 1, and boom, we've shown that p of n plus 1 is true. So hence we've shown that the proposition 2 to the power n is strictly greater than n, that is for all values of n in the set of natural numbers. So now this is going to hold for any value of n we take from the set of natural numbers. Thank you guys for watching, and I'll see you in the next video.